All right, hello everyone. This video may be a little longer than normal. It's two sections together. They're both a little shorter, but I have some calculator stuff again to show you, so I'll do the best I can going fast. But we're combining two sections and a little bit of calculator work. So influential points, section 3.4. So we've used this term outliers before, and it's a very vague term in a scatter plot, right? So an outlier is just a point separated from the bulk of the data. So like, does it look like it doesn't fit? And I'll show you this in a second. And that's just kind of an opinion. So rather than this term outliers, we tend to use this better term, mathematicians call influential points. An influential point is just like, does it influence what's going on? Does it influence the line of best fit? Does it influence the correlation? And to judge influence, what we're going to do is we're going to just take a look at a scatter plot. And if we think it might be influential, we're just going to take it out. And we're going to run all the numbers again and see what happens. So I'll show you a quick example of this. This is actually P21 on section 3.4. So I have some data, which I'm going to run through right here. You can see the data. It's data, some movie stuff. There you can see the data. 601, 1235 is the first point, 461, 319 is the second. And anyway, that's from that P21 on section 3.4. So the first thing I'm going to do is just draw a scatter plot of this so I can see it. So as a quick review, and I can't see all of it. Oh, maybe you can. We're going to go second function stat plot. Actually, before I do that, I'm just going to go to my y equals, make sure there's nothing in there, and there is. So we're going to get that out of there. And then we're going to go stat plot. And what we're going to do is we're going to do a scatter plot of that list 1, list 2. So make sure we're turned on. This is the scatter plot, the first one. It's going to change what it asks for. It's going to ask for 2 lists. Notice an X list and a Y list. So list 1 and list 2. For my scatter plot, you can put any kind of mark you want on it. And then zoom stat is typically the best way to start. For us, it might not be the best way, but if we go zoom 9, it usually gets us roughly where we want to go. And you can see that there's that point way out here up in the upper right that might look like it might be an outlier. Some people might say it's not an outlier because it looks like it might be on the line of best fit. And I'll go ahead and graph the line of best fit here for you in just a second, show you how to do that now, also, which I should have probably done in class anyway. Hopefully we did that. So I'm going to go stat, calculate a line of regression now. And we're going to go a line of regression on list 1 and list 2. No frequency list. We're going to clear that. We're going to store that regression equation because then we can graph it. Variables, y1. And now we're going to calculate it. And there's the line of best fit. So just keep that in mind. I have it written down on my paper, actually. It's 2.28 minus x minus 409. There's also a correlation. Sorry, I should turn my catalog on. Or sorry, my diagnostic on. So I'm going to do that. Hopefully I showed you this in class also. Probably a good thing that that happened, I guess. So now if I turn that on and then, whoops, we'll go calculate that line of regression again. We'll just do it again. We'll store the regression equation even though it's already in there now. And the correlation of 0.757, which I have written down right there for you. Okay, just so you know it. So now, actually, if I go back and go to the stat plot, whoops, sorry, just hit graph again, notice that the line of best fit will pop up on there for me. So there might be an argument whether that point is an outlier or not, because some people say it's on the line, some say it's not. I say it is an outlier because it just doesn't fit the data. But we're just going to take it out and see how it influences my graph. So we're going to go back to my list, stat edit here, and it's actually that first point in there. So we're going to delete the 601. And then we're going to bop over and we're going to delete the 1235. And then we're just going to run the numbers again. And we're going to go stat, calculate line of regression on list 1 and list 2. It doesn't really matter if I store it this time. I'm not going to use it again. And now you see y equals 0.03x plus 359 with a correlation of 0.018. So I have all those numbers written down just so you can see them. Quite a difference, right? There's the first one with the point in there, got a correlation of 0.76, completely different slope, completely different correlation. So we would say this point is influential, okay? There's no real guide for how much it has to change. So when we ask these problems, it becomes pretty obvious, I think, that there's some sort of big change going on. So that is called an influential point. All you do is take it out and check it. Okay. What we're going to spend the majority of time on here is what are called residual plots. And I'm going to show you how to do this in your calculator. So a residual plot is a picture, it's a scatter plot, but instead of graphing x and y's, it graphs x, so this would still be your x variable, but then it puts the residuals on the y-axis. So I'm going to show you how to do this on your calculator, and then I'm going to tell you what that residual plot does for us. Okay, so I'm using another set of data here. I just kind of wrote this data in here, so I'm going to bump so you can see this. We're going to go list 3 and list 4 is my data. It's just a little population model, so I'll give you a chance to write that down, give them your calculator. 1950, 1960, 1970, 1980, 1990. And those populations are like in thousands or something. I think it's 100,000s. Let's go 100,000s. I think it's in thousands. So 50,000, 67,000, 91,000, 122,000, 165,000. Just did a little rescaling, taking off the zeros. You can leave them in there if you want. Just remember that they're there because they're in thousands. So we could draw a scatter plot of this, but what we're going to do is show you how to do a residual plot. So you've learned how to take residuals. It's y minus y hat, right? So we're going to show you how to use the calculator to find those residuals now in an entire list. So actually, you know what? I'm going to do this the quick way. This is pretty cool, actually. So watch this. Rather than using, you can use lists to manipulate this, but I think that's a little too much work. So the calculator actually does it for us. It's pretty cool. So I'm going to go to stat calculate, and I'm going to run a line of best fit on those list 3 and list 4. All right. So we're going to go line of regression, and it's going to be on list 3 and list 4. I'm going to store that regression equation. It's important that we do that. Otherwise, it's not going to do the work for us. And then we calculate. So we don't know what just happened. The calculator did all the work for us, right? There's a line of best fit. So what we're going to do, the calculator actually figured out the residuals for us also. So watch this. If we go to my list menu, second function list, way down at the bottom here, you're going to, oops. I got it. You're going to see list 8, the residual list, RISID. If I just hit enter and hit enter just so you can see them, there are all the residuals. So they're already there for us, right? So now watch, if I go to stat plot, this is kind of cool. I know I get kind of excited about this, sorry. I'm going to do a scatter plot, but notice what I'm going to do is I'm going to go X list for list 1, and my list 2 is going to be my residual list. So I got to go back to my list menu, second function list, scroll down there to 8 again, and residuals for my Y list. And now when I go zoom stat, oh no. Oh no. Oh, I know why. I know why. You guys know why. So this is a good lesson, actually. This is called dimension mismatch. Dimension mismatch. It means I have a problem with my dimensions, which my calculator is trying to match up lists that needs the same amount of points. I think I know what I did wrong. If I go, let's quit this. Oops. If I go back to stat plot, I think I used list 1. List 1 was my whole other list. Remember, my X's for this problem were list 3. You were probably yelling at the screen as I was doing that, I'm sure, right? List 3 was my X's, and my Y's are my residuals. Probably a good thing that happened, actually. Oops. So let's quit that. And let's go zoom stat now, and hopefully it will work out. And we get what's called a residual plot. The middle line now is always 0 on the residual plot, by the way. And the x-axis is the x-axis. So here's what we're doing. So it turns out the residual plots are an important piece of information for us. If we look at the scatter plot, just so you can see it, I didn't show you this, but watch. If you look at and I didn't show you the correlation either, so watch this. But before I do that, let's do, oh yeah, we'll go back. Let's just notice there's a pattern in that residual plot. That's going to come see a little bit of pattern. Doesn't have to be a great pattern, but there's clearly some sort of pattern going on there, right? So if I go back, just so you can see it, and graph list 3 versus list 4. I didn't really do this, just so you can see it versus list 4. And we'll go zoom stat to graph this. You can see that a line looks like a pretty good model, okay? But it's actually a little curved. It's harder to see, but the line looks like a good model. And if you go back to the correlation, check this out, list 3 and list 4, it's got a pretty strong correlation of 0.98. However, that pattern in the residual plot, this is kind of the key thing here. Let me make this a little smaller so you can see it. So residual plots can often help us, sorry about that, see patterns that we don't see in the regular scatter plot. The regular scatter plot looked like a line, looked great. But it turns out if the residual plot does not look random or has some sort of pattern, it probably means the linear model is not the best model. Okay, so in a linear model, that scatter plot is going to look elliptical. It's going to be kind of scattered all over the place, or the residual plot would be scattered. Okay, but when we see a pattern, it's telling us that it's probably not the best model, that there's probably a better model. So they're going to ask this phraseology. They're going to say, is this a good model? What they mean is it the best model? The 0.98 might tell you it's a good model, but that's not really what they mean. They really mean, is it the best model? So now what we're going to do is this thing. So now there's a better model, okay? So we're going to do what are called shape-changing transformations. So I'm going to try to go through this a little quicker than I normally would because I know this video is getting long. Basically what we can do is we can take a graph that's curved and we can stretch it. Like if we just stretch the x or just stretch the y's, we can make it more linear. And we can do these transformations by doing things like square rooting y's or logging y's or squaring x's. Either any one of these things, this will make y smaller, right? This will make y smaller. This will make x's bigger. So if you're trying to make one bigger or both bigger or something like that, you can do one of these transformations to stretch the graph and make it more linear. And that's what we're going to do in this problem. The nice thing is you don't have to worry. These are all called power transformations or transformations to achieve linearity. You're not going to have to like do one of these on your own where you pick your own linearity transformation. We're going to do it for you. So what we're going to do is this. We're going to take this same data that this was the data we just used, by the way, 50, 60, 70, 80, 90. And we're going to do a transformation. What we're going to do is we're going to change the y's. Okay, we're going to shrink the y's to make it more linear. You can do this any way you want. The book's going to tell you, I'm going to tell you how to do it. No one's going to make you decide. So we're just going to plot x versus log y. So what we're going to do is take our data and transform it. And in this case, we're only going to transform one of them. We're going to transform just our x, or just our y, and leave our x's alone. Okay, so we're going to go, I'm going to grab a piece of paper here, sorry. We're going to go, we're going to transform that, x's and log y. So what we're going to do is this. We're going to go back to my list, all right? And we're going to go, we're going to leave the x's alone. So they're in list 3 right now already. But what we're going to do is we're going to go to list 5, and we're going to scroll up to the top of list 5, and we're going to go log. That was the transformation I wanted to do of list 4. Okay, log of list 4. So that's going to give me a transformed values for y's now. Okay, transform values for y. So now what I'm going to do is find the line of best fit with my new list. It's still, one of the old lists is the same. The x's are the same. So we're going to go list 3 and list 5. A lot of times we might have 2 transformations here, so my x might have a new list also. So now I'm going to go list 3 with list 5. I'm going to calculate a line of regression with list 3 and list 5. I'm going to store this regression equation because it's going to be pretty important for me to have in there. I'll show you why in a second. Y1. And now we're going to run this list. I'm going to write this down just so we can see it. I know you can't see this yet. Give me 1 second. Y equals 0.0129. I'm not going to worry about the rounding because it's sitting in my calculator for me, negative 23.5999. And now notice that R is 0.99997, much stronger, 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 right? Right. So this is my new equation, okay? What we're going to do now is use this equation to make a prediction. Just want to show you how to predict because this is usually the trickiest part, and then I'll be done. So let's predict the population in the year 2000. 10 more years. The model went from 1950 to 1990, notice, okay? So we have to be a little bit careful here because normally we just put 2000 in there. We are going to put 2000 in there for sure. But I want you to remember that this new equation is really log y equals 0.01297x minus 23.599. Okay, and if I had transformed my x's, that x might be like x squared or x to the 1/2 or something like that. So we got to keep that in mind when we solve the equation or when we plug in. So if x was really log x, we wouldn't plug in 2000, we would plug in log of 2000. But right now I am going to plug 2000 right into my line of best fit. Notice no rounding, okay? Really, really important, no rounding. If you round these numbers, you make a gigantic difference in your final answer. So we have to use that line of best fit in the calculator. So I'm going to go right back to my y variables, and we're going to use that y1, and we're going to plug in 2000. We're going to get out 2.34677. So right now, I get log y equals, a lot of people think this is y, 2.346779867. It's not y, though. So a lot of people circle that answer and go to the next problem. Think about it, that population was 2.34. Look at my list of numbers, right? Sorry, here they are for the population. 2.34 makes no sense for 2000, right? It's because we have to undo the transformation I've made. So this is the hardest algebra you do in this class. We have to solve this equation for y. Hopefully remember, you're going to do that by going 10 to that power. I'm going to go right back to my calculator, and I'm going to go 10 to the power of, sorry about my screen, answer, because that was sitting in there. And now I get my population of 222.21. Remember, that was in thousands, 222.21. I'll switch that in a second. But hopefully you'll see that that makes a little bit more sense, right? The 222 would fit that better. So I guess since I have 1,000, 2,222,100. So we have to undo that transformation that we made. So hopefully that helped. We'll go over that in class. I know the first time you see that's a little bit tricky, and I know that video got a little long. Sorry about that, but I'll see you in class.